Consider a mass spectrometer used to separate the two isotopes hydrogen and deuterium. The isotope hydrogen has a proton, and deuterium has a proton and a neutron. Assume both ions have a 1+ charge, and they enter the magnetic field region with a speed of 6.0 times 10 to the power of 5 meters per second. Calculate the magnitude of the magnetic field that is required to give a detector placement difference of 1.5 millimeters as measured from the initial entry point into the spectrometer compared to when the ions leave the spectrometer. So the first thing that I usually do is to write what we know. So in the second sentence, it says the isotope hydrogen has a proton and deuterium has a proton and a neutron. And this is basically giving you the mass of hydrogen and the mass of deuterium. So starting with the mass of hydrogen, I'm going to call hydrogen MH. So MH, which is hydrogen, it tells you that it has a proton. So therefore, the mass of the proton is the mass of the isotope hydrogen. So the mass of a proton is, from my formula sheet, 1.673 times 10 to the negative 27 kilograms. And as for the mass of deuterium, I'm going to call that MD for deuterium. And it says that it has a proton and a neutron. So therefore the mass is going to be the mass of a proton plus a neutron. So the mass of a proton is already 1.673 times 10 to the negative 27. And then if you add the mass of a neutron, that's going to give you the mass of a proton and a neutron. So the mass of a neutron is 1.675 times 10 to the power of negative 27. So just to make things simpler, I'm going to type this in my calculator and see what I get. Okay, so once you get your answer, you can replace this with what you got. So what I got was 3.348 times 10 to the negative 27 kilograms. That is a mass of deuterium. Now it says that assume both ions have a 1+ charge. So what does this information tell you? Well, if you look at the number 1+ charge, it's telling you that it's giving you the charge, and the charge is 1+. So plus, that means a charge of a proton, and the charge of a proton is 1.60 times 10 to the negative 19 coulombs. And since it's only 1, then this is the answer for the charge. If, for example, the charge was 2+, then you would need to multiply this number by 2 to get the charge. And finally, they're telling you that they enter the magnetic field region with a speed, so that's velocity, of 6.0 times 10 to the power of 5 meters per second. Now, the next sentence, it's also giving you hold on, I'm going to draw a diagram first so you know what's going on. So say this is hydrogen and deuterium. It's gonna go in this direction, and it says calculate the magnitude of the magnetic field. So it's basically traveling to the right and it's going into a magnetic field. And the magnetic field can either be into the page or out of the page. It doesn't really matter, but let's just say that is into the page, but it doesn't matter in this question what it is, but I'm just gonna say it's into the page so that we can draw the direction of the isotope. So if it's going into the page, you have to use your right hand rule to figure out the force that is acting on the isotope. So if it's going into the page, that means your fingers is going to be facing the computer, since that's into the page, and then your thumb is going to be facing to the right, since your thumb represents the velocity. So as you can see, well, you can't really see, but your palm is actually facing up. So the force is in an upward direction, which means that it's the direction of this isotope is going to go this way. It's going to go up. And then it's going to exit. Okay, so calculate the magnitude of the magnetic field. The magnetic field is given by B. And that's what we want to calculate. To give a detector placement difference of 1.5 millimeters. So this means that we know the isotope is going to get split. So first it's like one dot, and then it's going to be split into hydrogen and deuterium. So that means one of them is going to go like this. One of them is going to go like the one that I just drew. And then this difference over here, that is D. And it's telling you that it's 1.5 millimeters. And we want to convert that to meters. So to do that, just divide it by 1,000. So that gives you 1.5 times 10 to the negative 3 meters. Okay, so in this question, it's asking for the magnetic field, and to do this type of question, you just have to know one equation, and this equation is D equals 2R2 minus 2R1. And where this equation comes from, it comes from the path that the hydrogen and deuterium takes. So if you just look at 2R, that means it's 2 times the radius. So basically, essentially what is going on is this distance here. That's the radius is in the middle. So as you can see, there's the length of this is 2 times the radius of the larger radius. And then if you just look at 2R1, that is this distance. So it's the diameter of the path of the smaller radius. And if you look at the difference, here, that is equivalent to 1.5 millimeters. So that's where this equation comes from. And now instead of writing 2r2, let's replace that with h or d. So we want to have the larger radius first, and the larger radius is going to be given by the larger mass. So in this case, it's D, which is larger than hydrogen. And then R1 is the one with the smaller mass, which is hydrogen. And now I have to show another formula for radius to solve this problem. So let's start with some forces. Okay, so I'll just write the force first. What we want to use is Fm equals Fc. And the reason why we're doing this is that we can plug in some values for these and rearrange to get the radius. So why is Fm equals to Fc? Well, there's a magnetic force that is going up, and somehow that is making since the velocity is going to the right and then the force is going up, that's making the particle move in this direction. So that is it has a circular acceleration, therefore it's like a centripetal force. And what's causing that centripetal force? That's the magnetic force. So that's why they are equal. So if you plug in some values, the magnetic force is equal to the charge times the velocity, actually the magnitude of the velocity, times the magnetic field. And this is equal to ma, but this time we have centripetal acceleration, and that is equal to v squared over r. Now we want to isolate for r, so that's going to be mv squared over qvb. Now we're going to use this equation and plug it into the distance equation. So d equals 2. Okay, first of all, we can factor this, since in both things there's a 2 in it, so it's going to be equivalent to 2 times rd minus rh. Now we can start plugging things in. Rd is mv squared, and what m is it? There's only 2 options. The m, the mass of the deuterium, or the mass of the hydrogen. So let's go with the mass of the deuterium, since we're using the radius of the deuterium atom. And v squared, v is the same, so it doesn't really matter. I just realized something. The v squared actually cancels out, so over here, there's a V here, and then there's a V here. So that's going to give you mV over QB. Okay, so let's continue. Q is the same. Remember, it's +1. And B, of course, is going to be the same since it's going into the same magnetic field. Now we're going to subtract MH. Since we're using the radius of the hydrogen atom, V is of course the same, and QB is the same. Now we want to rearrange to find B, since that's what the question is asking for. And to do that, first I'm going to factor out the common things that we have. So V is common, Q and B are both common. So we've got MD minus MH. And now to just simplify things a bit, I'm going to do 2 times V times MD minus MH over QB. Now we can just isolate for B. That's going to be 2V times MD minus MH divided by DQ. So I just did it really quickly, but I just did it in one step, but if you want, you can do it in more steps. Yeah. So now we can plug in the numbers, and hopefully this will give the right answer. So V is 6.0 times 10 to the power of 5. The mass of deuterium, 3.348 times 10 to the negative 27. Minus the mass of hydrogen, which is 1.673 times 10 to the negative 27. So I'm hoping I'm doing this correctly. All divided by D times Q. So D, that's 1.5 times 10 to the negative 3. And Q is 1.6 times 10 to the negative 19. And you just plug this whole thing into your calculator. So I'm going to do it and see if I get the right answer. I hope I get the right answer. Yes, okay, I got it right. So what I got was 8.375. And we have to put this to the correct number of sig digs. So basically to do that, you look at the question and see which number has the smallest number of sig digs. Okay, so 1 plus, that doesn't really count because we're using 1.6 times 10 to the negative 19. And then the next one is 6.0 times 10 to the power 5, or 1.5. And both of them have 2 sig digs, so we're going to make the answer 2 sig digs. 8.4, and magnetic field is measured in Tesla, so this is the final answer. Consider a mass spectrometer used to separate the 2 isotopes of uranium, and then it gives you the mass of both of them. Assume the ions enter the magnetic field region of strength 9.5 Tesla with identical speeds, and leave the spectrometer with a separation of 2.2 millimeters as measured from the entry point after completing a half-circle turn. Calculate the initial speed of the ions. So, first thing that we need to do is write what we're given. So, if you see the 3 plus on the right of the uranium, that's telling you the charge. And essentially what this means, the plus means the charge of a proton, which is always going to be 1.6 times 10 to the power of negative 19. But in this case, we have 3 in front of it. So that means we have to multiply that by 3. So that means 3 times 1.6 times 10 to the negative 19. And that gives me 4.8 times 10 to the negative 19 coulombs. So this is the charge for both isotopes. And as you can see, the mass is different. So I'm just going to name the first one mass 1. And the second one mass 2. And of course, they're in kilograms. Assume the ions enter the magnetic field region of strength 9.5 T. So it's giving you the strength of the magnetic field, which is measured in Teslas. With identical speeds. So you know the speeds are identical. And then it's giving you the distance. 2.2 millimeters, we have to convert that to meters. So divide that by 1,000. That's 2.2 times 10 to the negative 3 meters. Calculate the initial speed of the ions. So we want to know the initial speed. And we're actually going to use the same formula since it's basically the same kind of situation. The formula is D equal to 2R minus 2R. And for the R, we want the one with the bigger radius to be first so that we get a positive number. And in this case, the mass with the bigger radius is mass 1. So we have radius 1 and then radius 2. And now we can just factor it out since we have a 2. And if you remember from the first example, the radius is equivalent to m. In this case, we're going to have 1 since it's radius 1, V over QB. And the way we got this was from making sure that the magnetic force was equal to the centripetal force and solving for R. And then R2 is going to be M2 times V over QB. And now let's factor this out a bit more. So things we've got in common is V over QB times M1 minus M2. And if we just simplify this, 2 times V times M1 minus M2 is divided by QB. Now the question's asking for the initial velocity, so that means we're isolating for V. This is going to give us D times Q times B over 2 times M1 minus M2. So I'm just doing this in one step, but if you want, you can, of course, do this slower than me. Let me just check if this is correct. Yeah. So now all we got to do is plug in the numbers. So D is 2.2 times 10 to the negative 3. Q, that's 4.8 times 10 to the negative 19. B is 9.5. M1, that's 3.952 times 10 to the negative 25 minus M2, which is 3.903 times 10 to the power of negative 25. And you just need to plug this all into your calculator. So I'm going to do that. Okay, and I got a really large number. I'll just write it down here. And for our final answer, we should make sure it's the correct number of sig digs. So let's look at the question. The mass is given by 4 sig digs. We're going to ignore the charge. And then distance is 2.2. That's 2 sig digs. And field strength is 2.2, also 2 sig digs. So 2 sig digs wins, and we're going to do this with 2 sig digs. And this is kind of big, so I'm going to use scientific notation. 1, 2, 3, 4, 5, 6 times 10 to the power of 6 meters per second. And that is the answer to this question. So the isotope, it's going to enter the magnetic field, with this initial speed.